What gravity really is. You think you understand gravity. Step on a scale. See the number. That's your weight. Earth pulling you down. Simple. Drop something, it falls. The moon orbits Earth. Planets circle the sun. Objects with mass attract each other. Newton figured this out centuries ago. But that simple picture isn't just incomplete. It's wrong about what's actually happening. Because gravity isn't a force at all. Once you see what gravity really is, the whole universe starts to look different. Let me show you. Stand up right now. Feel your weight. What are you actually feeling? You'd say, gravity pulling me down. But think about the real sensation. The floor pressing against your feet, pushing up. That's what you feel. The pshek. Always pushing up. Never pulling down. So where's this pull everyone talks about? You never feel it, not once. Here's something stranger. The moon is falling toward Earth right now. It's been falling for billions of years. But it never gets closer. It just circles, always falling, never landing. What kind of pull does that? A pull that never actually pulls anything in? And according to Newton, that pull acts instantly. Move the Earth. And the moon feels it immediately across 240,000 miles of empty space. How? What carries the signal? Even Newton couldn't answer that. He called it action at a distance, and admitted he didn't understand how it worked. But the math was beautiful, and the predictions were perfect, so people stopped asking. They shouldn't have. A history of careful looking centuries ago, nobody understood how planets moved. Copernicus said they orbit the sun. Fine. But how? What paths do they follow? Tycho Brahe built an observatory and spent decades recording the positions of planets, night after night, year after year, measuring angles to fractions of a degree. Why such precision? Because you can't understand nature by guessing. You have to look, measure carefully, and write down exactly what you see. That's where real science begins. Tycho's data eventually reached Johannes Kepler, who set out to find the true shape of planetary orbits. He tried circles first. The predictions were close. But Mars was off by 8 arc minutes, a tiny fraction of a degree. Most people would call that measurement error, but Kepler knew Tycho's instruments were better than that. So he threw out his theory and started over. Years later, he found the answer: ellipses. Planets move in ellipses with the sun at one focus, a perfect match to the data. But it raised a bigger question. Why ellipses? Meanwhile, Galileo was rolling balls down ramps. Sounds trivial, but watch what happens. A ball rolls down an incline, speeds up, then rolls onto a flat surface and keeps going. It doesn't stop right away. Now imagine no friction at all. The ball would roll forever. Same speed, same direction forever. This bothered people. Surely motion needs a constant push. Surely things naturally come to rest. No. That's stasis. Beskianchuis. Motion is the natural state. A moving object doesn't need an explanation to keep moving. What needs explaining is change. Slowing down, friction, speeding up, a push, turning, a sideways force. This is inertia. Newton's first law. And it creates a puzzle. Planets should move in straight lines. That's their natural state, but they don't. They curve. Something must be deflecting them every instant. What? Newton's answer. Newton saw it clearly. Planets want to travel in straight lines. That's inertia. But they curve instead, so something is constantly changing their motion. He called it gravity, a universal attraction between any two masses. The strength depends on mass and distance. More mass means a stronger pull. More distance means a weaker one, falling off with the square of the distance. With this one idea, everything fell into place. Ellipses appear because a planet is falling toward the sun while also moving sideways. The two combine into an elliptical path. Kepler's laws fall directly out of Newton's force law plus inertia. The The moon orbits Earth for the same reason. It's falling, but moving sideways fast enough to keep missing. It falls around Earth instead of into it. An apple falls for the same reason too. Same force, same law, just a different scale. Newton calculated how far the moon falls every second compared to a straight line, and how far an apple falls near Earth's surface. Once you account for the difference in distance, the numbers matched perfectly. The force pulling the apple down is the very same force holding the moon in orbit. Heaven and Earth, one physics. From there, everything started making sense. Tides, from the moon pulling on Earth's oceans, Earth's slight bulge at the equator from its spin, comets returning on schedule since they follow elliptical orbits too, strange anomalies, found explanations, Jupiter's moons appearing early or late, led to the first measurement of the speed of light. Small wobbles in Uranus's orbit led astronomers to predict an unseen planet, and they found Neptune exactly where the math said it should be. For 2 centuries, Newton's law of gravity stood as one of science's greatest triumphs. It explained everything anyone could measure. The one detail nobody could explain: drop a hammer and a feather in a vacuum. They hit the ground at exactly the same moment. The hammer has more mass, so Newton's gravity should pull it harder, much harder. But the hammer also has more inertia, so it resists acceleration more by exactly the same amount. The two effects cancel perfectly. Not approximately, perfectly. Every object falls at the same rate no matter its mass. Why? Newton's theory needs 2 separate properties of mass. A gravitational mass that determines how strongly something is attracted, and an inertial mass that determines how hard it is to accelerate. For every substance ever tested to extraordinary precision, these two are exactly equal. Why should they be equal? Newton had no answer, just a remarkable coincidence that happened to make the math work. Or was it a coincidence? Einstein's question. Einstein asked, what if it's not a coincidence at all? What if that perfect equality is a clue about what gravity really is? Try this thought experiment. You're in a sealed room with no windows. You feel your normal weight pressing you to the floor. Are you standing on Earth? Or are you in a rocket accelerating upward at 9.8 meters per second squared, out in deep space? Drop something. It falls to the floor either way. Throw a ball sideways. Same curve path either way. Step on a scale. Same reading either way. There's no experiment that can tell the two apart. This is the equivalence principle. If gravity and acceleration are truly indistinguishable, maybe they're the same thing. Maybe what feels like sitting still in a gravitational field is actually a kind of acceleration. Here's Einstein's leap. Objects in free fall have no force acting on them at all. The falling apple, the orbiting moon, a satellite circling Earth, an astronaut floating in a capsule. None of them feel any force. They're simply following their natural path, with nothing pulling on them. But the apple is clearly falling, isn't it? Yes. But what if the apple isn't accelerating at all? What if it's following the straightest possible path, and it's space itself that's curved? Gravity as geometry. This is Einstein's central insight. Gravity isn't a force between objects. It's the curvature of space and time. A massive object doesn't reach out and pull on other objects. It warps the space around it, bending the very geometry everything else moves through. The apple isn't being pulled to the ground. It's following the straightest possible path through curved space-time, and near Earth, straight points toward Earth's center. You, standing on the ground, aren't being pulled down either. You're trying to follow your own natural path through that curved space-time, toward Earth's center. But the ground is in the way. The ground pushes you upward, away from that natural path. That push is what you feel as weight, not a pull from below. a push from below, stopping you from falling. Einstein's theory made a testable prediction. If gravity is really the curvature of space, it should bend light too. Even though light has no mass, and in Newton's theory, massless things shouldn't feel gravity at all. During a solar eclipse, astronomers measured the positions of stars near the sun's edge. The stars appeared shifted from where they should have been. Their light had bent on its way past the sun, exactly as Einstein predicted. We now call this gravitational lensing, and we see it throughout the universe. Massive objects bending and distorting the light of things far behind them. Falling. All the way around. Astronauts in orbit look weightless. Is that zero gravity up there? No. At the altitude of the space station, Earth's gravity is still about 90% as strong as it is on the ground. So why do astronauts float? Because they're falling. The whole capsule is constantly falling toward Earth, but it's also moving sideways at around 17,000 miles per hour, fast enough that as it falls, Earth's curved surface keeps falling away beneath it. It keeps missing the ground. It falls around Earth instead of into it. Since everything inside, astronaut, capsule, water droplet, camera, falls at exactly the same rate, nothing presses against anything else. No weight, no sense of up or down. It feels exactly like floating freely in empty space, far from any mass, because in a real sense, it is the same thing. Free fall in a gravitational field and floating in empty space aren't just similar. They're identical. In both cases, no force acts on you. You're simply following the natural geometry of space-time. Why Earth is round? Here's something else this explains. Why is Earth round in the first place? Not because some force pulls everything toward a center, squeezing it into a sphere. It's because the space-time around Earth's mass is curved equally in every direction. Every rock, every drop of water, is following the straightest path it can through that curved geometry. And when matter follows those curves equally from every direction, the result is a sphere. The one shape where every point on the surface sits the same distance from the center. Earth is round because that's simply what happens when matter follows curved space-time. The shape isn't imposed from outside. It emerges from the geometry. An ant walking what it thinks is a straight line across that curved surface is, from the outside, actually tracing a curve, even though to the ant, it feels perfectly straight. That's exactly what's happening to everything moving near Earth. One force, not two massive objects, create dips and wells in spacetime. The sun a deep one, Earth a smaller one, even you a tiny one, far too small to measure. Anything moving nearby naturally follows those curves, not because something is pulling it, but because it's taking the straightest path the geometry allows. The moon orbits Earth because that's the straightest path through Earth's curved space-time, and the geometry happens to bend that path into a circle. An apple falls because, in the curved space-time near Earth's surface, straight ahead points toward the center. A thrown ball traces a parabola, not because something is pulling it down, but because it's moving through curved space-time, and a straight line through curved space looks, to us, like a curve. Stand up again and feel your weight. In Newton's picture, two forces are balancing. Gravity pulling you down, the floor pushing you up. In Einstein's picture, there's only one force, the floor pushing up. And that means you must be accelerating. You are constantly upward, away from the natural path your body would otherwise follow toward Earth's center. The floor never stops pushing, so you never stop feeling weight. An apple hanging on a branch is being pushed upward in exactly the same way, by the branch. When the branch breaks, that push stops, and the apple is finally free to follow its natural path. It falls, but it isn't accelerating. For the first time, it's moving naturally, with nothing acting on it at all. Standing still takes a force. Falling is what happens when nothing stops you. From apples to black holes. Once gravity is geometry, the most extreme objects in the universe start to make sense too. A star is a massive ball of gas, and its mass creates a deep well in spacetime, with every natural path pointing inward. What keeps it from collapsing is the outward pressure from nuclear reactions in its core. When the fuel runs out, that pressure drops, the balance breaks, and the star collapses. If the star is massive enough, the collapse keeps going until matter is crushed to incredible density, atomic nuclei merging, electrons crushed out of existence. What's left is a neutron star, nuclear matter packed into something the size of a city, dense enough that a teaspoonful would weigh 1 billion tons. For even more massive stars, not even that can stop the collapse. Space-time curves so sharply that every possible path leads inward, even for light. That's a black hole. Light itself, following the straightest path it can through that extreme geometry, spirals inward and never comes back out. We can't see black holes directly, but we see their effects. Matter spiraling in, heating up, and blazing with energy before it disappears. One idea, everywhere. All of it comes from one principle. Mass curves, space-time, and objects follow the curves. From that single idea comes everything. Planetary orbits, ocean tides, the slight extra wobble in Mercury's orbit that Newton's theory couldn't explain but Einstein's predicts exactly. Gravitational lensing, black holes, even the ripples in space-time we now detect when massive objects collide far across the universe. The same idea that explains the moon's orbit also explains galaxies and galaxy clusters. The same pattern repeated at every scale. Newton's equations still work beautifully for practical purposes. We use them to launch satellites, plan orbits, predict eclipses. They're simpler than Einstein's, and accurate enough for almost everything we do. But Einstein showed us what gravity actually is, not a mysterious force reaching invisibly across empty space, the curvature of space and time itself. Mass tells space how to curve. Curved space tells objects how to move. So the next time you step on a scale, remember, you're not measuring a pull from below. You're measuring how hard the floor has to push to stop you from following your natural path through curved space-time. When you watch something fall, you're watching it finally move freely, following the geometry that mass has woven into the fabric of reality. And when you look up at the moon, you're looking at something tracing the straightest possible path through the curved space around Earth, a path that looks, from here, like a circle. Gravity was never a pull. It's geometry. And that's far more beautiful than any mysterious pull could ever be. Don't forget to subscribe to the channel and like the video for more content like this.